The fourth topic in week 1 is the concept of function. So we will start with an important definition. Say we have two sets, call them capital X and capital Y. Given two sets, capital X and capital Y, we define the idea of Cartesian product, the Cartesian product of X and Y written X cross Y, little cross times Y, X times Y, simply is the set is defined as follows. It is the set of ordered pairs. Ordered pairs are written in round parentheses in mathematics, and for pairs, unlike sets, the order is important. So X cross Y is the set of ordered pairs. We can write A comma B, where A is in X and B is in Y. So the first coordinate comes from the first set, X is the first set, the first coordinate comes from the first set, and the second coordinate comes from the second set. It should be clear immediately from here that in general, X cross Y is not the same as Y cross X. Let's see some examples. We can multiply two one-element sets, say set containing 1, Cartesian product with set containing 2, simply is the set containing one pair, 1, 2. If you multiply set containing elements 1, 2, 1, 2, by another set containing two elements, say 3, 4. The result will be a set containing 4 pairs, right? So you take an element from the first set and form a pair of that element with each of the elements of the second set. So it'll be 1, 3, 1, 4, and then the same with the second element, 2. It'll be 2, 3, and 2, 4. It should be clear that definition doesn't depend on any numbers, and in fact, the elements of our sets that we multiply need not be numbers. I can, for instance, consider the following example. I can multiply a set containing 3 elements, say an asterisk in a circle, a box, and a cross, I can multiply this by a set containing one element, namely the empty set. The product will be a set of 3 pairs. One pair will be the asterisk in a circle, comma, the empty set. The second pair, or rather another pair, there's no order here, there's no first pair or second pair. Another pair will be the box, comma, the empty set. And yet another pair will be cross, comma, the empty set. The concept of Cartesian product. All right, once we introduce the idea of Cartesian product, we should be able to introduce the idea of relation. A relation let's call it R, and relation is defined from a set to a set. From a set X to a set Y. And I should have these words in red because this is part of the definition. A relation is simply a subset of the Cartesian product X to Y. So it simply is a set of ordered pairs. Now, if little x is in capital X, and little y is in capital Y, right? If the pair X comma Y is in our set R, we will write, for some reason, we will write this as, not as X comma Y is in R, but rather as X, R, Y. Or sometimes X tilde Y. Here the first set, X, is called the domain of R. And the other set, capital Y, is called the codomain of R. Nothing prevents us from considering the situation when X and Y are equal. In this case, instead of saying that R is a relation from X to X, we will simply say R is a relation on X. A relation from X to X is called a relation on X. Let's look at a simple example. Let's consider the set of ordered pairs. The following set of ordered pairs. One comma two, 2 comma 4, 3 comma 6, 4 comma 8, and 5 comma 10. And note that this is a relation because from where to where? Because this is a subset of the set 1, 2, 3, 4, 5 cross product 2, 4, 6, 8, and 10. Note, by the way, that this cross product will have 25 elements, and our set only has 5 pairs, right? A relation need not be the same as the cross product. A relation is a subset of the cross product. Right? So here, the set 1, 2, 3, 4, 5 is the domain, and this is the codomain. Okay, once we have introduced the idea of a relation, we can introduce the idea of a function. All right, a relation from x to y is called a function if there's a very simple condition satisfied. For every x in the domain x, for every y and z in the codomain y, whenever x is related to y and x is related to z, it follows immediately that y equals to z. In other words, every x in the domain can only be related to at most one element in the codomain. In other words, a function is a relation in which every element of the domain is related to exactly one element of the codomain. Now, there is special notation for relations that are functions. If a relation f from x to y is a function, we in this case write the following construction: f colon x arrow y. Also, we will write y equals f of x instead of xy belongs to f, relation f, or x f y. Here, of course, x is in x and y is in y. And this condition above can be written slightly differently using this other notation. So in a function, from x to y, we have for every x in x, for every yz in y, if it so happens that f at x equals y, and it so happens that f at x equals z, necessarily y must be equal to z. Of course, not every relation is a function. Every function is a relation, but not every relation is a function. And let's see some examples. Let, in this example, A be a set 1, 2, 3, 4, and B be the set 1, 2, 3, 4, 5. And define relation F from A to B the following way. F is the set of pairs, ordered pairs, where the first coordinate is from A, the second coordinate is always from B. 1, 2, 2, 2, 3, 4, and 4, 1. And we can easily see that F is a function. Why is that? Why is F a function? Well, F is a function because every first coordinate from A is paired with exactly one with exactly one element of B. Right? In the set F, every first coordinate 1, 2, 3, and 4 corresponds to exactly one coordinate from B. 1 corresponds to 2 and only 2. 2 corresponds to 2 and only 2. It's all right that 1 and 2 correspond to the same second coordinate. That's fine. We only require that every first coordinate be paired with exactly one second coordinate. We can visualize this graphically using sets. So that is set A. It has elements 1, 2, 3, and 4. And that is set B. It has elements 1, 2, 3, 4, and 5. We can match pairs. 1 corresponds to 2. And 2 corresponds to 2. 3 corresponds to 4. And 4 corresponds to 1. Here the domain of function f is the set A and simply is the set 1, 2, 3, 4. Now let's look at another example. In this example, f was a function. Here's another example. In this example, we again introduce two sets, A and B. A is the set A, B, C, D, E, and B is the set 1, 2, 3. And we define F, relation F, from A to B via the following set: A1, A2, B1, C3, and D3. We see immediately that f is not a function. Why is that? Why is f not a function? From A to B. Well, that is because we have two reasons for that. One problem is the element E of the set A corresponds to no element of B. In other words, f is not defined at E. E in A corresponds or is paired to no element of B. You may think this is a minor problem because I could just forget about E altogether and consider the set ABCD. But even then, f wouldn't be a function from A to B. We have a bigger problem. We have A corresponding to two different elements of the set B. Lowercase a corresponds to 1 in B and 2 in B. That is a much bigger problem. Right? We have A and A paired simultaneously with 1 in B and with 2 in B. And of course, 1 and 2 are not equal. So that is an example of a relation that is not a function. All right, a little bit more terminology related to functions and relations. When we talk about functions or domain, functions or relations, mainly functions, elements of the domain will be called, the collective name for the elements of the domain will be the independent variable. Mainly, we will use the letter X for that. The symbol lowercase x will mean the independent variable. Or sometimes called the argument of the function. So when somebody says argument of the function, they mean the independent variable, the expression of the variable to which the function is applied. Another idea, the image of a function or range. As the argument x varies throughout the domain, the corresponding values of the dependent variable y form what's called an image of f, or range of f. The value y, which is f of x. Called the image of x under the action of f, under f. Varies, of course, depending on the values of x, and for that reason y varies depending on x. So y will be called in this context the dependent variable. If we collect all possible values of the dependent variable, we get the image of the function. The special notation for that we will use is Im of f, or you can say f applied to the domain x, f of capital X, not to be confused with lowercase x, column equality. Well, the formal definition is y in the codomain such that there exists an x with the property that x in the domain and y equals f of x. It's an overly formal definition. We can make it simpler. Image of f being again f of capital X simply is apply f to every element of the domain, x and x. Now, we will occasionally use the following notation. Technically, when you define a function, you always have to say what the domain and codomain are. But occasionally, or in fact very often, we will not specifically say what the domain and codomain are, in which case we will write the following thing. We will write x maps to f of x. This symbol means maps to. Whenever it's clear from the context what the domain and codomain are. Finally, we will introduce the idea of equality of functions. We say two functions are equal. f1 and f2 are equal. And write, of course, f1 equals f2. If they have equal domains as sets, if their domains as sets are equal. And for every x from this common domain, for every x in the domain f1, which is the same as domain f2, we have f1 at x equals f2 of x. f1 equals f2, equality of functions. All right, finally, I'd like to say a few words about the idea of graph for relations and functions. It'll be a simple definition. The graph of a relation f from the set A to the set B. Specifically this time I require that A and B be number sets. So A and B are elements of R. It will be the set of all points in the plane, the set of all points in the coordinate plane xy, set of points in the xy plane, such that a point A comma B, a point with coordinates A and B, written in parentheses A comma B, is in the set if and only if the pair AB is an F. We will have a graphical example in a moment. Moreover, if the relation is a function, the graph is simply the set x comma f of x in parentheses, where x runs over the domain of f. Let's get to an example. We'll draw two pictures. One picture will be the graph of a function, and we will discuss why one picture is the graph of a function while the other picture is not. And the other picture will look like this. So here, for instance, we have the point A comma B in the set. In fact, this graph was meant to be the graph of the function 1/6 x cubed minus 1/2 x squared minus 1/6 x plus 1/2. And this graph on the right corresponds to the equation y squared equals x cubed minus x squared plus 5. And here I have, say, if this is A, this is A comma B, and this is A comma C. And we can see that the graph on the right corresponds to a relation which is not a function, because the first coordinate A from the domain corresponds to more than one pair in the relation. We have A comma B in the relation, and A comma C in the relation. Yet, clearly, B and C are not equal. Why the graph on the left is a function we will discuss later when we get to a vertical line test, and also the vertical line test will explain why this picture is not the graph of a function. All right, that's it for the concept of function.